NASA releases a ton of new images of 3I Atlas. New research claims to overturn dark energy. Chinese astronauts don't have a safe way to get home, and the solar system might be moving faster through the universe than we thought. All this and more in this Space Bites. Well, the shutdown is over, and that means all of the images that NASA took with all of its spacecraft during the shutdown are now available. And NASA just released an enormous number of pictures this week. So we got images from Mars Reconnaissance Orbiter, images from Perseverance, Lucy, Psyche, and then a whole bunch of spacecraft that are observing the sun, like SOHO and Stereo. So we're going to get into this now. So the big one that obviously everybody wanted to see was the images from the Mars Reconnaissance Orbiter. And this is because Comet 3I Atlas came within about 30 million kilometers of the planet Mars. And the best telescope at Mars is on board the Mars Reconnaissance Orbiter. Now, normally this spacecraft is designed to look down onto the surface of Mars, but it can look at other objects in space and has actually taken images of the moons, Phobos and Deimos. And these are tricky because these are moving. The spacecraft is moving. It's got to be able to keep its optics aligned on that target. And so when Comet 3I Atlas was making its closest approach in September, it was a natural fit. Unfortunately, this happened during the government shutdown. But fortunately, the astronomers had sort of calculated everything, put in all of the instructions to take these pictures, and now we've got these images available. Now, I'll warn you, they're not great. And that's because it is still like a sub half millimeter telescope on a spacecraft that's designed to look at the surface of planet Mars and not observe comets. But you can definitely see more detail in this image than you saw with the ExoMars and with the Perseverance, which is taking pictures from the surface. But then we got some great images from the spacecraft that are looking at the sun. So two are the SOHO and the Stereo A spacecraft. Because they're equipped with coronagraphs, able to block the light from the sun, they're able to watch as the comet is passing by. And this is during the fastest point of its approach through the solar system. It's reached the very bottom of its path through the sun's enormous gravitational well, and the comet is going 209,000 kilometers per hour, which is just a ludicrous speed. We got some images from NASA's Psyche mission, which is on its way to go and see asteroid Psyche, and then its Lucy mission. With the Psyche mission in September, we got 4 observations of the comet moving through space. And so you can see sort of 4 distinct locations for it. And this is really important because trying to track the exact position and movement of the comet is very important, because then if there was some kind of off-gassing that was changing its velocity, then these are the kinds of things that you would detect as it was making its closest approach to the sun. And the Lucy mission was able to actually reveal some details on the tail. Now, NASA has built an entire page dedicated just to their ongoing observations of 3I Atlas. So they go all the way back to the first images that we saw from James Webb, from Hubble Space Telescope, and then this flurry of new images that we got from all these different spacecraft. And we're going to see more, much more. So this page, bookmark this page, and then you'll be able to see new images as they come in. Now, I want to shift gears and talk about a new paper that is going to make a lot of you dark energy haters really happy. And that is that there is possible evidence that dark energy isn't real. But I'm going to need to provide a whole bunch of qualifiers and need to follow Paul Sutter's law, which is that if it's interesting, it's probably wrong. So let's go back and let's talk about lambda cold dark matter. Cold dark matter, this is the series of observations that there is some kind of invisible mass in the universe, or gravity doesn't work the way we understand, but it is most likely some kind of cold, massive particle that doesn't interact with regular matter or with itself except through gravity. That's the CDM in the lambda CDM model. The lambda part, this is the observation that happened about 25 years ago, where astronomers were measuring the distances to Type 1a supernova and found that the actual expansion of the universe seems to be accelerating, that there is this cosmological constant, or lambda, that is present, dark energy, and that this is going to cause the future universe to accelerate and accelerate at ever-increasing rates. But there's growing evidence that the expansion rate of the universe hasn't been accelerating in the way that we might think, that instead maybe this amount of dark energy that is in the universe has been changing over time. Maybe it was stronger early in the universe and it's weakening over time. all of these observations rest on the Type 1a supernova. And so you have to make sure that you're doing your observations of the Type 1a supernova and that these need to be standard candles, which is that, when a Type 1a supernova goes off, it detonates with roughly the same amount of energy. And so if you know its intrinsic brightness, then you can know how far away this object is because you measure its current brightness, you know what its brightness should be, that tells you the distance. But there's been this controversy or this idea that maybe Type 1a supernova aren't constant, that the brightness of Type 1a supernova have been changing over time throughout the age of the universe. And so a new study is suggesting that there is a correlation between the brightness of a Type 1a supernova and the age of the galaxy that it's within. And so the younger the galaxy, the fainter the supernova will be. And so that would explain why those galaxies seem to be farther away than we thought. They're not farther, it's just that the Type 1a supernova going off in those galaxies is fainter. And so the astronomers say that when you measure that correlation and then you punch all those numbers in, the observation of dark energy just goes away, and to a very high degree of sigma, like 9 sigma. And so they say that there is no dark energy. It's just that the younger the galaxy, the one seen early in the universe, the fainter the supernova. So that's it? No dark energy? Well, not so fast. And there are some serious concerns with the paper. And in fact, we did a 4-part series on this on Universe Today. We're putting a link to all 4 parts in this. And in the last part, Dr. Brian Koberlein, who is our tamed astrophysicist at Universe Today, had a conversation with Adam Rees, who is the Nobel Prize winner who contributed to the discovery of dark energy. And he says there's a couple of issues with this paper. This idea of the age of the galaxy. Now, it's very difficult to determine the age of a galaxy, but you can determine the mass of a galaxy. And in fact, it looks like the mass and the age of the galaxies correlate quite strongly. And this correlation is so strong that the existing databases of supernovae account for this mass discrepancy. In other words, that when you've got a supernova in a different galaxy, the normalized data for that supernova in the big databases like Pantheon Plus, it accounts for the mass of the galaxy. And that's a way that astronomers can take that into account when they're doing their calculations. But for this study, the astronomers didn't use the modern database of supernova. Instead, they used an older one that didn't have that mass accounting for in the data. That's kind of unusual. Why wouldn't you use the good database that everybody uses instead of this older one of a smaller number of supernova that isn't as good? But the bigger issue is it appears that Type 1a supernovae are found in star-forming regions in galaxies. But typically, these Type 1a supernovae, the progenitor star, is less than 1 billion years old. And so the age of the galaxy kind of has nothing to do with the age of the star that went off. That you're going to see new star-forming regions in galaxies that are nearby, and they're going to produce Type 1a supernovae. You're going to find galaxies that are almost at the age of the universe, and they're going to have star-forming regions, and they're going to produce Type 1a supernovae. And so there would need to be some way that the entire galaxy itself has been enriched or not enriched with certain amounts of chemicals, and that's having an effect on the brightness of the supernovae or the dust that's being produced or something like that. Now, this is a very preliminary result, and there is a lot of skepticism about this result. So I'm going to do a sort of longer rant at the end of this episode to sort of tell you why you should be a lot more cautious about this kind of result, and just in general. Don't get too excited about scientific results, but you should definitely read this 4-part series by Dr. Brian Koberlein. 2 weeks ago, we reported that a piece of space debris impacted the crew capsule for the Shenzhou 20 crew. Now, this is the return capsule that is on board the Chinese space station. And so the new crew of taikonauts, the Chinese version of astronauts, flew to the station and then came on board. And so there were 6 people on board the station. And then the old crew was going to take the 20, the one that they had arrived at, back down to Earth. But because of this piece of space debris, there was like a cracked windscreen on the capsule. The Chinese Space Agency decided it's probably not safe to bring them home in that vehicle. So they used the 21, the Shenzhou 21 to come back. So now you've got 3 taikonauts on board the station and they have no safe, reliable way home. So this is temporarily a bad situation, but the plan is to send the next capsule the Shenzhou 22 to the Chinese space station, and that was going to have a crew. Now they're going to send it uncrewed, and so then that will give them their way to be able to come home. We've got more details about this from Matt Williams on Universe Today. Every week, we do a vote on our channel where you tell us what you thought was the best space news story of the week. And the winner last week was the launch and successful recovery of the booster for New Glenn. So thank you everybody who voted. Now we're going to post the new poll into the post tab here on our channel. So if you want to see them, make sure you subscribe to the channel, click on the notifications bell, and then go into the post tab and just vote for a whole bunch of our polls. And then that should train the algorithm and you'll get more of those and less people just doing TikTok dances on your Shorts feed. So we are moving around the sun at about 30 kilometers per second. And the solar system is moving through the Milky Way at about 230 kilometers per second. But when you add all of the motions of the solar system, you actually get its motion relative to the cosmic microwave background radiation. This is called the cosmic microwave background dipole. And it makes sense that, when the light from the cosmic microwave background radiation was released, it was released in all directions and it got redshifted over time, but the solar system is moving through the universe. And so the stuff that we're moving towards is going to be slightly less redshifted, and the stuff we're moving away is going to be a little bit more redshifted. And astronomers have calculated that speed at 369.82 kilometers per second. So that is the speed that the solar system is moving through the universe, which is just amazing that we know this. But there are other ways to measure the motion of the solar system. And so astronomers thought, well, what if we measure it based on our motion compared to background galaxies? And so they're looking for a specific kind of galaxy that is very bright in the radio wave. It's called a radio galaxy. And they said, well, we're going to do this survey of the sky, and that we're going to measure the most distant number of radio galaxies that we can detect. And so in the direction that the solar system is moving, we should be able to measure a few more galaxies than the direction that the solar system is moving away from. So they made these observations, and indeed they did find one. And they found that it correlated with the CMB dipole, roughly, to within about 11 degrees. So it's roughly in the same direction. But the weird mystery is that they calculated that it's moving 3.7 times faster than the measurement from the cosmic microwave background radiation. And so if true, this would have serious consequences for cosmology. Obviously, the first possibility is that it's not true, that it's a measurement error, that there's dust, always dust, and other systematic errors. But it could be that there are more local galaxies and they're not arranged in this sort of equal shell around the Milky Way. Or at the largest structure, the universe isn't as homogeneous and isotropic as we expect. So you would expect at the largest scale, when you're looking out to, 5+ billion light years away, that although the individual galaxies are going to be different, it's going to sort of kind of look the same in all directions. But maybe the universe isn't as sort of uniform as expected. And that would be very exciting. And that would challenge a lot of the ideas in cosmology. But again, if it's interesting, it's probably wrong. So stay tuned for more on this one. And we've got a great article from Mark Thompson. Now we'll talk about black holes. Now you're probably aware of this prediction by Stephen Hawking that black holes should give off excess thermal radiation. This is known as Hawking radiation. And I could do a whole video explaining, what is the cause of Hawking radiation. But the bottom line is they generate temperature. They have entropy, which is sort of another way to talk about the temperature of the black hole. And there are a whole bunch of laws of thermodynamics that we follow all the laws of thermodynamics in this house, but when you apply those laws to black holes, you get sort of modified versions of the laws of thermodynamics. And one that is really important is that the temperature or the entropy of a black hole is determined by the surface area of its event horizon, and that you can't have that number go down below the surface area of the black hole. And so a prediction is that when you have two black holes that merge, you should get this conservation of the total amount of entropy, the temperature that is coming off of the new merged black holes. It can't be less than the sum of the two black holes that made it up. And this has actually been a very tricky observation to make. But now astronomers have had two examples of gravitational waves released from colliding black holes where they're able to measure the surface areas of the two separate black holes and then measure the surface area of the combined black hole. And they found that it follows this law within about 99.5%. So it's, it's not the gold standard sigma, it's a 5 sigma, but it's still pretty good and showing that the black holes still follow the laws of thermodynamics. And we've got a story about this from Brian Coberline. That's a lot of really great space news this week. And in fact, there's one more big story to try and explain an unfolding mystery about how we might have an explanation for those really massive galaxies that we're seeing early on in the universe. Now, we think that the viewing experience over on Patreon is so much better than what you have here on YouTube. There's no ads. You get an email notification every single time we release a new video. And I'm not talking about having to pay us. It's all completely free. And so we make the longer version, which we call Space Spice Plus, available over on Patreon. So you can go, I'll put a link in the show notes. You can just go watch that episode right now. And then, and here's the pro tip, become a free member on Patreon, again, free, and then follow the Universe Today channel on Patreon. And then you'll get an email every single time we release a new video. And that way you're not waiting for the YouTube algorithm to decide that it wants to show you our videos, or maybe it doesn't anymore. So yeah, definitely go. Patreon.com/Universe Today. If you want more space news, we've got a ton of stories over on our website, Universe Today, of which I am the publisher. Usually 30 to 40 stories on Universe Today every week. We only have time to cover, like, I don't know, 8 here. So there's many more stories. But obviously you don't want to come and check out the website every couple of hours to find out if we've got a new story. So I write an email newsletter on every Friday that combines all of the stories that we're covering into one big document. And I write every single word in the entire thing. It's completely free. We don't have any advertisements there, like we have no advertisements anywhere. So definitely go and check that out if you want just like the comprehensive one-stop shop. I want all the space news that Fraser thinks is important and nothing more. Go to universetoday.com/newsletter to sign up. All right, so I'm going to give you some important caveats about this dark energy story and try to vaccinate you for the controversy that is about to happen, as well as to help you be prepared for when this kind of thing happens in the future. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bielok, Stein Nielsen, Dark Finger, Dave Verabeth, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, Nordspace, OneSafeForAnimals.org, Paul Robach, Ring Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So there is a lot of skepticism about this result. And I think you're going to see a lot of people say, that's it, dark energy has been disproved. It's really important that you understand this initial result. It's very exciting, but we need to be more careful and wait for all the evidence and let the peer review process play out. And that's what you're going to see now. You're going to see every single part of this result get picked apart by other astronomers, and they're going to question it, as they should. And we'll get to this place where we'll have a scientific consensus on whether or not this is actually disproven dark energy, which I'm sure will make a lot of you very happy, or dark energy is held up yet again. And I think the general lesson that you want to learn here is that you need to temper your excitement either way. And if you feel in your heart that dark energy isn't a thing, and you don't like it because it just doesn't feel right, then you're going to be biased towards the kinds of studies that reinforce that perspective. You're going to be excited by the studies that tell you that dark energy isn't real. You're going to look for reasons why the ones who tell you that it is real, this is just the consensus, this is just groupthink, this is just what everybody says, that you're going to be biased. And the thing you need to do is you need to just hang back and just relax and just enjoy the ride. And don't have a preconceived notion about how the universe works, because it just doesn't feel right. The universe does not obey our gut. It just does what it does, and our job is to figure out what it's doing. So stay tuned. Obviously, I will be reporting on this. All right, we'll see you next week.